Alright guys, let's take a look here. Catch up to you guys. So this one shouldn't have been too crazy here, the distance between these two. Distance formula is something you guys should know. Good old Pythagorean theorem. So how does it work?
y2 minus y1 squared.
Yeah, you could do 3 minus x or x minus 3 either way. Plus. Yeah, so it'd be x squared plus 1. So you keep going that way. And it doesn't matter because I'm squaring it, so who cares? The square makes it not matter. Let me stop there for a second, Zach. Is that true? Now, if I was asking you to find the max or min of this, then I would maximize or minimize d squared. I don't know if you guys remember that. That's probably going to happen to us somewhere this semester or something like that. Right? If you maximize d squared or minimize d squared, if you minimize d squared, that also minimizes d. Does that make sense? And why would you round it? Yeah, because you have the derivatives. You want to leave that big-ass square root in there? Hell no, because that would be a chain rule. So not only would the inside already disgusting, it would also involve taking the derivative of the whole thing to the 1/2 power. You guys kind of follow what's happening? Does this sound familiar? You use d squared to do optimization problems for distance and not just big-ass square root shit, right? We don't want that. Is it? All right, slowly coming back. I'm not asking you for any of that here, by the way. Some of you guys look at me crying, I'm crazy now. Where did it say to minimize it? No. If I was going to, I would do that. So here, you just leave the square root in there, and you can simplify this down. What's this x squared? 6x and 9. x4, 2x squared, and 1. And then you just put your like terms together. All right, 3x squared, x to the 4th, 3x squared, minus 6x, plus 10. Is that everybody? Looks like it. Is that cool? There wasn't much else to do beyond that. Hopefully, if you went a step further, I'd be curious to see what happened. One of the quickest ways to make a teacher cry, a math teacher cry, is related to this problem down here. Oh my God. If I see this from anybody, if you've written that, just take tonight and do a mantra or something. This is not this. Square root of 9 plus 4 is not equal to 3 plus 2. Right? This ain't 5. This shit. This is square root of 13. So the square root is a power. It can't distribute across subtraction, can it? And that's what you're doing if you do this. So please, hopefully everybody listen, this is wrong. Don't say this is what my math teacher wrote. No. When he said it was wrong, yes. So what's the only thing you can do? Yeah, take a 4 out of the inside, and of course it'll come out as, no, it has to be a 4 there, Jeff. It'll come out as 2, and then the other stuff is just left in here.
Oh, I did something right.
Cool. That's it. It looks like the inside desperately wants something done. You're like, I'm sorry, buddy. Just do damn bad. Because it would be x minus 2, x plus 2. There's not 2 of anything. Oh shit, too bad. Okay, maybe. All right. Let's go back. So I don't know. At some point in your history, you should have seen this extended 3 dimensions. Obviously, we're going to be living. We currently do live in 3 dimensions that we can see. Some a lot others that we can't see. But you should have seen the extension of this, and it's the same thing, right? How do I find the distance between these points?
2 plus 5.
Yeah, 2 minus negative 5, so 2 plus 5 squared plus 3 minus 0 squared plus squared. I like it. It's the same thing. If I had 4 points, if I lived in 4 dimensions in this problem, you just add another little squared piece in there. Is that cool? And yes, if you go further, if you get to linear algebra, anybody have to take linear? Anybody already taken linear? Some of you guys might have already taken linear, so you know what I'm about to say. And who needs to take linear subject? All right. You'll be talking about n-dimensional space. You'll be talking about 80 dimensions, 150 dimensions. Math doesn't care, right? You know, like I know math doesn't care. But math doesn't care how many dimensions you want it to live in. It's fine, right? Has anybody ever heard of string theory or M theory or something like that? The math is actually a little behind where it needs to be. So That's kind of neat. That would be where I would do research if I was going to do research, is getting the math to the point where you can do the physics. Because the physics is all like, come on, math, we need you. And we're like, oh, shit. Anyway. That's what it sounded like. So then what are you going to have to do on this? 58, 67? 67. We're at 67. All right. That's a nice one. Nice concrete number. Nice. Now this one, it's purely, do you remember, so a lot of times people remember the integral of secant squared, because what do I take the derivative of to get secant squared? Tangent. And if you remember how to think, the cos stuff is always negative. It's symmetric. It's a nice analogy, but it's always negative. So if the derivative of tangent is secant squared, the derivative of what is cosecant squared? Negative cotangent. I love it. So the integral of cosecant squared is negative cotangent. You could maybe break it up and do some weird identity bullshit, but it's just a direct. This is a one-liner. Negative cotangent theta, and of course, plus cosine theta, because the derivative of cosine theta is negative sine theta, and of course your infamous plus c. So pretty cool with that one? So you got to remember your trig derivatives, right? You got to know those, so you can do your integrals quickly. Now, let me build up to part B here. What's the derivative of this? That's a. Give me a second. Yeah, a e to the ax. And where did the a really come from? What part of the procedure? Chain, I heard chain. That's what I was waiting for. It's a chain rule, right? Derivative of e to something is e to the thing, and then the thing gets a term, right? So the derivative of ax is a. Now people try to extend this. If it's e to the ax squared, they say, well, then it's going to be a. No, it's bullshit, because now the derivative of the inside, it's quadratic. It's going to have a 2 times blah, you guys. So don't try to think too much about this. The a didn't just come down. It's because of the chain rule. That's why it's there. But what I want to talk about now is, what would the integral of this be then?
Is it 8?
Yeah, it wants to be this, but then you have to divide by the a that would come down. I love thinking about. I love thinking about. When you integrate, you think about, well, what would come out, and if it's not there in the original problem, I got to kill it, right? So inside the integral, there is no a in front of the e. So if the answer was just this, then there would be an a coming down. I don't want it there, so I just put an a on the bottom to kill it. So when I say, no, you're dead. All right, and then it works out. Now you could do u sub on this, but I definitely want you guys to be past the point where we got to do u sub where the internal function is linear. No, do you guys see what I'm saying? The internal function there is ax. It's linear. You should not need. If you do it, I'm not going to take points off, but you really should be past that, right? Now, remind me this. What's the derivative of 2 to the x? There you go. Natural. And of course, this is related. This is why e to the x is its own derivative, because ln e is 1. But then what does this mean? Integral of 2 to the x must be then. Same idea as before.
2 to the x over.
2 to the x over. Because I want to kill that ln2 that would want to come down. Does that make sense? And this one is weird. There is no u sub to do here. This would be a lot more complicated substitution. It would be reproving the reason the interval is what it is. You just got to remember it's the opposite relationship, right? Because the interval is the opposite process. So how does that relate to this? Well, what's integral 7 to the x?
7x over
ln7, I like it. And of course,
3
natural log of
absolute value of absolute value.
Because what is the domain of 3 over x? What's the domain of 3 over x? Everything except 0. If I did not put those absolute values, would the domain of my answer function match the domain of my input function? No. That would be a big problem, wouldn't it?
Negative.
So you can integrate 1 over x on either side of 0. The absolute value will say your ass. And it's got to be there. Does that make sense? So that their domains match, right? Without it, their domains don't match. And that's a little point, but it actually becomes huge in some problems. It's the whole reason why some problems work, and people forget that actually happens. All right, how we doing so far? Okay. All right, so then I gave you this one. Yes, it's totally U sub. Can't be trig sub y. So squared. And then you might think it can't be U sub, but what I hate about the way U sub is taught is normally it's not, the entire flexibility of U sub is not shown. So I don't know if some of you guys saw problems like this and you started to realize, since it's really just substitution, I need all my X shit replaced with U shit, right? Like, oh, Dean, you should call them shits? No, Dean, go ahead. I want the X shit replaced with U shit, right? So there's a lot more flexibility to it than it feels when you first learn about it. So obviously I want to let U equal what? So what does that mean? If I solve this, what I just wrote, I'm letting that be true. Therefore, what must be true? Solve for x. X must be equal to U plus 1. So then I can replace. Now here, I'll show you fully what I do. And then I'll actually backtrack on what I do. I just want to show you. This is what I do as a student. I did this. I made this up myself. I said it's not really 1 and 2 because what are 1 and 2 related to? X. And I'm about to replace them with U's. So you could change the limits, or you could just change everything back to X at the end. And normally that's what I did as a student. It doesn't really matter. Mathematically, they're equivalent. But if you don't like what I'm doing, then do it the way you do it. It's fantastic. So what does this become now? This X is now U plus 1. And this X minus 1 is now, I like it. And now it's du. Because what's du? Yes, I love it. Because it was just a straight up relation, just a directly related. Is that cool, you guys see that? So really, the real problem with this stupid problem is, if only the inside had been x to begin with, then I could write it as x to the 1/2, and if that outside x would have been x minus 1, I could have just distributed it. So here we say, we want the inside to be a single thing, not 2 terms, 1 term. So then we force that to be true. We make the inside of that sucker a single term. How are we doing so far? So you guys look perturbed, but oh well. It's the first time you're seeing this kind of thing, then just to incorporate it into what you know. And the minute I write something like this down, I've defined what U is in terms of X. That means I know what X is in terms of U. You can always use that if it makes sense, if it works, if it helps something out. And here it's totally necessary to do it. So now I've got the inside of my radical as 1 term. I can distribute it now as I could not do before. That's really why that kind of works. So then you get what now? You get integral, not quite 1, not quite 2, of what? Yeah, U to the 3/2 plus U to the 1/2. And what does that become? What is your budget? Oh, yes. Yes, so this becomes, I don't know if you guys remember the shortcut, if anybody ever showed you, when you integrate, you add these two, right? 3 plus 2 is 5, so it'd be 5 over 2. And then the coefficient, you don't need this anymore, Jeff. You know, then the coefficient is going to be 2/5. I love it. The reciprocal of that, of course, right? So then this 1 plus 2 is 3. So now this is U to the 3/2. And then 2 over 3, I like it. And I want to go from not quite 1 to not quite 2. Now I can just throw back in what U is in terms of X. All right, so it'll be 2/5 X minus 1 to the 5/2 plus 2/3 X minus 1 to the 3/2, 1 to 2. So when I plug a 2 in, this is 1, 1, that's awesome. So we get 2/5 plus 2/3. When I plug a 1 in, everything's 0. That kicks ass. So what's 2/5 plus 2/3? Yeah, 16/15, right? Cool. Do you guys know how to use the calculator to check that? Has anybody never seen the calculator integrate? Everybody's seen that? Okay, all right. I'll take your word. Okay. So then these guys should be relatively quick based on what you know. So whenever I have a cosecant, I don't have those memorized, but I know how they relate to the ones I do. So cosecant, of course, is 1 over sine. And in what quadrant am I in? Uh-oh. Quadrant 2. I'm not quite pi, right? I'm not quite a full 1/8. I'm pi over 6 away from pi. So I'm just still in the second quadrant. So sine there is positive. And the reference angle is pi over 6. So that's how I would immediately rewrite that. Now we have a different way you do it. Beautiful. But you got to capture all those ideas. And of course, what's the sine of pi over 6? The way I think about it is sine does not like x, it likes y. So if it's close to where it's not like it, it's going to be small. It's going to be like the troll is barely. So it doesn't like it down here. So it's 1/2. Up here, it likes it up there. It's rad 3 over 2. Here, it's like right down the middle. So it's going to be rad 2 over 2. Does that sort of jive? That's the way I look at it. So this is 1 over 1/2, which is 2. Amazing. And this one's not too bad. Cosine negative 2 pi over 3 I'm in quadrant. So isn't that almost pi back? That's pi over 3 away from being a full pi back. So I'm going to be in quadrant 3. So I did hear a lot of you guys say quadrant 3, but I heard a few 2s and 4s. What's that?
Negative 1. Negative doesn't influence it, right?
Say again?
Negative doesn't influence it. You can take your...
Totally. So you could use a trig identity. What's cosine of negative theta?
Cosine theta.
So which one would it be?
Cosine theta.
Ooh, I got some dissension. I like it. So let's think about it. Cosine of 30 versus cosine of negative 30. They're going to be the same. I like it because it's all about x, and x is in the right this hemisphere where it's positive. Is that cool? That weird way to say it? That side of it? Cool. So that the cosine does not affect it. So you just kind of take the negative away. I like it. Or you just think it's back 2 pi over 3. Right? I'm in the third quadrant, because otherwise where would I be? I would be in the, if I went this way, I would be in the second quadrant, and the answer is going to come out negative either way. I like it. So this is going to be negative cosine of, what would the reference angle be? Yes, pi over 3 away from a full pi.
4 pi over 3.
No, reference angle's always got to be less than 90. I like it. So what's cosine of pi over 3?
Negative 1/2.
Yeah, this will be where cosine doesn't like it up there, right? So it'll be negative 1/2. Now again, dear God, guys, if you don't like the way that I look at it, if you have a different way you look at it, beautiful. Just show me something. Show me some kind of idea of where these things are coming from. You with me? Show me something that's showing me where you come from. Because if you make a simple mistake and I see your work, you're not going to lose many points. But if you make a mistake and I don't see any work at all, I got to assume the worst. I like it. So if you have a different way of thinking about this kind of thing, you do that way. I love it. You don't have to do it the way I did it. I don't care. Whatever way makes sense. Now this is the one that I thought that a lot of us would have trouble with.
Over here,
All right, let's find out. Yes.
create a triangle.
Yes, beautiful. So, investigate what that inner thing represents. What physically would the inside here, what would it have to represent, really? Yeah, you could draw a representative triangle that contains what this is, but what is this? It's a what? It's a line, it's an angle, right?
Yeah.
Inverse sine is going to have as an output what sine normally has as an input, right? That's how inverse functions work. So the output for inverse sine has got to be an angle. It's the angle where the sine would have the value 5 over 13, right? So if you don't quite believe me, so if I have inverse sine, what was it, 5 over 13?
Yes.
Equals an angle, right? Now take the sine of both sides. What happens then, of course? I took the sine of both sides. So what happens then? These two kill each other. Because the idea of inverse function doesn't give a shit what the function actually is. They just kill each other. So then I have sine theta equals 5 over 13. So without doing all that work I just did, anytime you have an inverse trig of something, you can draw the representative triangle. So what's the representative triangle going to be? Well, here's theta.
Hypotenuse 13.
Yeah.
And opposite is 5.
And now it's asking me what's tangent of that thing.
Sine over cosine.
You guys see that? Does that sound familiar? That's something you guys did back in 176, and it wasn't really made a big deal out of, but kind of thing you should be able to piece back together for yourself if you needed to. So the tangent of the angle, I have to know the left side. Hopefully some of you guys know it's a 12, 13 triangle, right? So then the tangent would be 5 over 12. Beautiful. So those of you who were saying that earlier, cool. I just wanted to catch up to you. I like it. So I really want you to understand, obviously, this is not representative of all of the math you should know coming in here. But a few of these problems are related to big mistakes people make. Obviously, I wanted to put some trig down there because that's something. Some people have made it through calculus without ever having taken trig. Yes. And it's because their teacher didn't make sure that trig problems were in there. And it's not a matter of just making problems up that have trig functions in them. Because hopefully some of you guys understand trig functions are stupid important to the real world. My God. So if you just have a few real world problems, you're not going to be able to escape trig functions. All right? So if you've had teachers that have not given you many trig problems, I'm sorry, you better freaking catch back up with your trig. Alright, so we're going to have quite a few trig stuff in here because we're going to learn different coordinate systems. Spherical coordinate systems, cylindrical coordinate systems. They're going to be using all these interesting angles defined in different ways. You don't want the sine of 30 degrees to be the problem, right? You want, what the shit is it, where is it, you want that to be the problem. Not remembering what those things are, right? You got to know those things. Okay. Anything on this sheet that I didn't cover well enough? That was a problem. Okay. So just as a little preview, and then I'm going to let us out of here just a tiny bit early. One of the very first things we're going to do, besides learning how to use 3D graph paper to plot some points, is to talk about how vectors can be used to create an entirely kind of different way to look at some things, a more generalized way to look at some things. So a vector, so I have the point 1, 2. There's the point 1, 2, right? The vector 1, 2, which we write like that, so to make it really clear, ooh, I got pointy stuff on the outside, so it must be a vector. The vector 1, 2 would actually be this. It points to that point if you put the tail at the origin. So I could pick that bad boy up and put it anywhere. It would still be the vector 1, 2. Because if I put it at the origin, that's the point it would point to. So the name of a vector is the point it would point to if you put the tail at the origin. Is that? So the tail, of course, is at the origin. The head is where the arrow is. You guys got it? So a vector has two things that a point does not. The vector has direction, and it's got length. Because if I had the vector 1, 3, that would be a little bit longer than the vector 1, 2, right? So its length means something. So if it was a force vector, The vector 1, 3 would represent a more powerful force than the vector 1, 2 would. And they're acting at slightly different directions, slightly different angles. Is that cool? So vectors will now be our basic units of what we're not numbers, but vectors will be our basic building blocks we're going to be playing with. So we are going to do build vectors. We're going to talk about what will a line look like if I use vectors. What would a plane definition be in terms of vectors, right? And vectors make a lot of mathematics so much freaking easier. But of course, you're not going to believe me for a while because you got to get used to the things themselves and how they're used to define things. So that's a really quick intro to what we're going to get into. So Wednesday, we're going to do our little field trip. Come by my office to see me if you need some help on whatever. And if you need an ad code, come on up here. I'll give you an ad code.